Hi, it's Serg. Yeah, I work for Syngenta, agronomic agribusiness, a global agribusiness company, um, and I look forward to talk to you about interpretable machine learning. And thank you for the introduction. Let me share my screen. Um, So, hold on, and show. There you go. Okay. Hopefully you can see it already. Thank you for your patience. I didn't have this set up. All right. So welcome to my session. Thank you for joining. My contact information is there. Feel free to reach me if you have any questions directly. I'll be asking questions, of course, after this session. So let's dig in. Oh, and also, given the broad audience, I won't get too deep into the weeds, but I welcome technical questions. So here we go. Before we begin, let me quickly introduce myself. My name is Serg Masis. Serg is my English nickname, but you can call me Sergio if you speak Spanish. I'm a data scientist at Syngenta, where I work on food security problems for the Climate and Agronomic Decision Science Department. For the last 10 months, I wrote a book for PAC that is a comprehensive hands-on overview of interpretable machine learning. It was just released 1 week ago, and it's available at Amazon. This is actually my second career. I think I heard people just before entering the session talk about web development. I was for 10 years a full stack web developer, an app developer, a webmaster, and even the founder of the search engine. I think probably this connects to that, as I'll be talking a bit about that. In this roles is how I got into analytics, since the internet is often the source for big data. So first, I like to start with a story. Actually a few stories, so bear with me. I will connect them to machine learning interpretation. Um, so the first story concerns Python. So for the last few months, I have been promoting the book before it was released. I've gotten quite a few people reach out to me with questions like this one. What ML algorithms to use, or this one, can you explain which model is better? As well as all of these ones, which are similar, all about algorithms, machine learning models, what libraries to use. And of course, these ones, which are a little bit more like a specific, what to use, PyTorch or TensorFlow, NLTK or spaCy, And then, of course, the age-old question, which is better, Python or R? So, of course, we know the answer to that question. Python, of course. Python is awesome. We import libraries that give us all kinds of superpowers. As you can see here, Python can make you fly, of course. You just have to import anti-gravity. I don't know if you've done that, but please try doing that. It's really fun. So, but we must remember one thing. Python, as great as it is just a toolbox. It's a nearly bottomless, magical toolbox, but it's a toolbox nonetheless. So that's probably a sacrilegious thing to say at a Python conference. So before you all chase me out with pitchforks, please allow me to explain. Asking a data scientist a question like this one is like asking a plumber if he uses wrenches and plungers. The answer is simple. We just simply use the best tools for the job out of those available in our toolbox. If you already program, learning how to use them is relatively trivial. What matters the most is why we use them. So this brings me to the first point, which is when it comes to data science, the why is always more important than the how. I will now let you into a short story of why I know why matters most. Some of you might be too young to remember 1999. But it was the year of the Matrix, the Fight Club, SpongeBob Bob SquarePants, Britney Spears, Star Wars Episode 1, and the craze for something called Y2K. You can look it up. I won't explain it here, but everybody was in a panic about that. It was also the first year, it was the year of my first paid job. I was a web developer back when most people dialed up and websites looked like this. Horrendous, right? And browsers were so different, you had to tailor websites to them. They could look entirely different or not work at all on different browsers. Certainly don't have that problem now. So I also learned to code HTML by hand, before web development software made it easy to do with drag and drop or higher level coding that abstracted it. Then, of course, came data-driven websites, which I would do in Perl, Confusion, Cold Fusion, Java, PHP, and connecting it to databases in Oracle, MySQL, Sybase, SQL servers, and Access. Back then, if you wanted a content management system, an e-commerce site, a customer relation management system, you would have to do the code from scratch. And I did. Now, for over 15 years now, it's pretty much inconceivable that someone goes through the trouble of making most of the most common forms of websites needed by scratch. Even when they do make custom applications, most of the low-level code has been abstracted by frameworks like Django, Laravel, Angular, Ruby, Flask, CodeIgniter, whatever. So to recap, back in 1999, there were a lot of problems a web developer had to be concerned about. Some were with the user devices like limited screen size and slow internet, not to mention browser compatibility, but this also had to do with with standards compliance. In addition to that, there were some major bottlenecks with servers and ISPs, and even the internet as we know it. Being so new, a lot of programming language frameworks and development platforms became quickly obsolete. Lastly, the tools used by developers hadn't consolidated, and it still was largely a manual process. So these problems were mostly fixed, right? Hooray. No. As you know by now, web developers just sit back and relax since the internet runs itself. Not really. With so much out of the way, they focus on improving their products, making them easier to use, more profitable, safer, more reliable, etc. In other words, fulfilling the mission of their organizations, the why. And in fact, AI plays a big role in a lot of that as well. So after I got bored with web development, I switched careers to data science. But it's deja vu. The reason I'm telling you the story is because I've been here before. When I see code, of data preparation steps, model training, and evaluation in Python, it takes me back to the days where all websites were custom, artisanally crafted, if you will. And who among us doesn't get giddy in anticipation while our model is training? This takes me back to when we waited a few minutes while website pages loaded. The feeling is one we take for granted now, but we surely don't miss. But when it comes to work, we spend a lot of time configuring libraries that can become incompatible, debugging minor issues, and looking for answers in Stack Overflow. This takes me back to the days when website content could make a browser crash and become easily unstable with a new version or something like that. But all this pain is temporary. Because what if I told you that the future of AI and machine learning is low code or no code? And much like everyone and your grandmother can now create a website in an idiot-proof interface and deploy it with one click, models will be able to train and deployed just as easily in a few years. Soon enough, writing code to train models with Python will seem like as quaint as writing HTML code to create websites. But before this becomes a reality, we must address the elephant in the room. In the early days of the internet, had tons of technical hurdles. And so has AI overcome many, but it still has a few more large ones to overcome, namely interpretability. And that's what this session is about. So I'm going to offer another analogy to where we are in machine learning. And I would argue that we also have a lot in common with the aviation 70 years ago. The inspiration for this comes from this article. This is a 3-year-old article. It's really good. You can look it up. It turns out machine learning and AI in general right now has many parallels with civil aviation 70 years ago. There has been hype about it for decades. It's finally more accessible to the masses. It's magical, and practitioners, well, are regarded magicians. I've actually had an agronomist in my company call me a magician. And in my previous company, a financial planner called me a wizard. But we better not get this praise get to us. I'm no Gandalf. It's no more wizardry than flying is thanks to physics. Also, because it has yet to reach its potential, it's a new frontier, and all the organizations that regulate the industry have yet to be born. Machine learning projects have an issue of taking off reliably. Likewise, in the 1940s and early 1950s, it was dozens of times more common that flights got delayed, redirected, or canceled than it is right now, not to mention turbulence and issues with limited flight distance and connections. These were very common, and we take it for granted now, but it happened a lot. Of course, there were also crashes. You could say machine learning has had its fair share of blunders over the last decade. I could fill dozens of slides with news clippings like these ones, represent only the ones we know of. There's a publication called AI Now that keeps tabs of them in case you're interested, but they happen a whole lot. Yeah, and the early history of commercial aviation was filled with high-profile catastrophic events. The high proportion of deaths over millions of passenger kilometers made flying an extremely deadly activity in the early years, especially considering that commercial planes didn't carry as many people. And now, believe it or not, it's the safest mode of transportation. Incidentally, AI, I know it's not killing people, at least yet, but the ways it causes harm are mostly more subtle and more widespread. So, how did aviation improve? First of all, several regulatory bodies were created in the early 1950s and started to ensure safe use of the airspace and aircrafts, allowing the greater public to trust this new mode of transportation. International standards were created from everything from structural integrity to aerodynamics and pilot licensing and certification. Speaking of which, in the early day era of flying, most pilots were Mavericks that performed acts to impress crowds on the ground. And even after World War II ended in 1945, there was a surplus of fighter pilots that could be enlisted for civil aviation. But capable as they were, the daredevil mindset of fighter pilots did not suit the mission that they had to be retrained. Lastly, instruments. More and better instruments. When safety is involved, you cannot get enough of them. Be honest. Which plane would you rather fly? The one to the left or the right? Seriously, which one? As for machine learning, we may have to wait a while before most governments enforce comprehensive AI regulation and international organizations and industry leaders enact standards. But you know what we can do in the meanwhile? Get in the habit of using better instruments. So these are the tools that the most common diagnostic interpretation methods and tools, and there are even more. Problem is, we tend to focus heavily on only predictive performance, which is the first one on the top, when there's so much more that we could learn and improve in the model if we use the rest. While using predictive performance alone is good enough under perfect conditions, it's like learning to fly only on clear days and then winging it when it's cloudy. That's a recipe for disaster. Then there's a flip side to diagnostics. This is how you fix issues that you find with the diagnostics. And I'm not talking about strictly performance issues, but those related to the main concepts of interpretable machine learning. So the main concepts of interpretable machine learning are fairness, accountability, and transparency, or FAT. It's fairly simple. You expect a machine learning model to produce fair predictions. They must be robust and traceable back to something or someone, and you should be able to understand exactly how they were made. There are many ethical concerns associated to these concepts. As you can see here, H1 connects to these three concepts. And ultimately, what we want to know is, can we trust the model? Well, aviation would have taken over the world without all of our collective trust. Not just the trust of, in this case, the aviators, but also the passengers. And when it comes to AI, the passengers are the people that use AI products. And believe me, they're losing trust. And trust is mission critical. As a transhumanist, I, for one, dream of an era of mixed reality and assistive augmentation where smart glasses or biohacked appendages can interface with us through thoughts and gestures and help both disabled and able-bodied people. But how would we trust AI to empower us in such an intimate way if right now it seems to bring out the worst in us? So it's fair to ask, is interpretable machine learning and ethical AI the same thing? Not really, but both concepts overlap. Ethical AI, also known as responsible ML, encompasses much more than interpretable ML because it includes data and algorithmic governance aspects. These aspects include privacy regulations, data management procedures, and even modeling standards. They uphold FAT. On the other hand, interpretable machine learning is how we implement fairness, accountability, and transparency with machine learning. However, these very same tools can be used for ethical reasons, can be used with no ethical reasons in mind, simply for curiosity, and they can also be used unethically too. So ethics aside, why would we need interpretable machine learning? Machine learning interpretation is needed because machine learning by itself is incomplete as a solution. Think about it. Simple problems could likely be solved with procedural programming. Solution covers all of it. The complex problems we optimize with machine learning require linear algebra, calculus, and statistics precisely because we don't understand all of the problem. By explaining the decisions of the model, we can cover gaps in our understanding of the problem, its incompleteness. One of the most significant issues is that given the high accuracy of our machine learning solutions, we tend to increase our confidence level to the point that we think we fully understand the problem. Then we're misled into thinking our solution covers all of it. So indeed, I believe overconfidence has curbed the adoption of interpretable machine learning amongst practitioners. They would think, well, if my model or my insights are so great and they tend to be true, why bother? Unlike the plane analogy, there's really no barrier for entry for using more and better instruments. So why wouldn't we use them if they're already freely available? Problem is, we have the following assumptions that lead us to become overconfident. So bear with me. Like here we have descriptive analytics. We have that truth. There's a truth that is, in machine learning, we first start, by exploring data and deriving insights through descriptive analytics. But this is not the only way to learn about the data. A model can discover much more, and we can use interpretation tools to this end. Once it's time to train a model, we change a single metric when the problem calls for much nuance. Maybe a fairness metric, maybe a cost factor. Often the incentives are only there to shoot for accuracy and nothing else, but at the expense of fairness, accountability, and transparency. And it is true that AI is eating up software, and software engineers are gravitating by the droves into AI and machine learning. But a machine learning model is not what I would call software. Yes, it's ones and zeros, but it's not deterministic in the same way software is. I'm not bashing engineers here. I have an engineering background myself, and we need more software engineering principles, but without the deterministic mindset. Soon enough, most models won't be even trained with code, but with drag and drop interfaces. So it shouldn't be seen as programming either. So what is it? It's statistics. And what you do with the statistics, you interpret them. We make predictions and imagine that a human won't take them at face value. But that's exactly what happens, which is why this human needs to understand what influences this prediction and how confident the model is about it. Also, wouldn't it be refreshing if the model could abstain from a prediction and not support it with a statistically sound margin of error? It's really common for us humans that when someone asks us a question, we say, well, I'm not sure. I'm not confident about it. I don't know. Why should a model should always be determine an answer? It's forced to make an answer even if it doesn't comply with certain confidence bounds. So the next one is, I'm sure we're all aware of this one, but the minute our model produces 99% accuracy or a very low MSE, we forget about it. It's entirely possible for all the decisions, predictions, or insights to be right for the wrong reasons, or to be right now, but wrong tomorrow, or to be right in the wrong way. Let me explain. Trusting the model is rarely about the model. Let me repeat that. Trusting the model is rarely about the model. We derive meaning and predictions from a model or the data directly from that is supposed to represent the truth. The most fundamental problem we are aware about is bad data. Typically, data entry errors, random if we're lucky. However, there are also biases associated to bad data we should control for. And anomaly detection methods and comparing with the external data sets for issues and distributions can help correct these issues. By the way, biased data doesn't always involve people. I deal with crop data in agriculture, and there's bias there too. As for truth, we have a whole host of issues. We have the ugly truths, all the prejudices and systemic biases that exist in the world, and our data is merely depicting. We can make sure our models mitigate them. Our models don't have to reflect the truth that exists. It can reflect the truth that we want. We also have fake truths and the many ways models can purposely be tricked. And the truths change over time and geography, but often models have no notion of this. Of course, spatial temporal models excluded. All of these issues only aggravate data issues. Lastly, we have our own biases with our models. Chief among them, observer bias, when we blind ourselves to what we assume or we want to be true. So the choice is yours. You can be a daredevil, chase after a few metrics and hope for the best, or through better instruments, understand the data conditions better and tweak the model for smoother, safer, and more reliable operation. Also, let's stop making predictions about only following trajectories, but possibly even changing them. There's a fitting quote that says, the best way to predict the future is to create it. It's often attributed to Abraham Lincoln, but it was Alan Kay of Atari that said it. So, if there's any Gen Xers in the audience, they know what I'm talking about. So now I'll make this last part a quick overview of how to incorporate interpretable machine learning. So this is your typical machine learning workflow. Many of you will be familiar with it. You first start with problem understanding, then data understanding, then data preparation, then modeling, then evaluation, then you do deployment, and then once it's deployed, there's inference on that deployed model. So the way I suggest is that once you've done some data hygiene, you can explore some, you can perform some exploratory modeling to let the model tell us what features matter the most and how they matter and how they interact. This would of course be a different process for image and text data, but very analogous. From these insights, you can iteratively combine features with feature engineering and remove some feature with some feature selection. This will produce a rough draft of a model that performs well enough. Once you have settled on features, or at least have a short list to test, you can create an optimized model through hyperparameter tuning. The key here is sparsity. You want a model that will generalize well, because otherwise you'll have something that won't work well in the real world. Evaluation ought to be extended not only to include performance with holdout data, but test for robustness with perturbed data, uncertainty with sensitivity analysis, and bias testing as well. It's very important to use error analysis tools for this sort of thing as well. Usually data isn't static, so you have to have a pipeline test for changing data, which is called feature and concept drift. Then you can retrain the model on this data and deploy it if it passes evaluation. Last but not least, and this is very important, whenever the model delivers a prediction, it should be automatically returned, which is what is called a local interpretation method, which tells the end user why this particular prediction was made, including confidence intervals. So it's very common when we would deliver a prediction, it's just whatever that prediction is, and there's no explanation to why it was made. I think this is wrong. I think this should change. I think it should be standard to come with an explanation, and a thorough explanation at that. And as I said before, I'm also advocating for abstention, especially in cases where there might be unfairness involved or some high consequences, because a lot of these things on a case-by-case basis can have very big consequences for people involved, such as loan applications, judgments in criminal cases and so forth. And so now I have a bit of conclusions. So interpretable machine learning has a synonym, which is explainable AI. And it's gaining growing popularity, as you can see here with academic publications, and then also with book publications. And here it is with search trends. But I don't think this is a trend or a fad. I honestly think this is the future of machine learning, because machine learning depends on this just as much as the future of aviation depended on better instruments. That's something really important, because a pilot now can, sit back and simply relax, because and be there when obviously things start to go wrong. They have to maybe manually pilot the plane, but for the most part, they just sit back. And the only reason they can do that is because they have good instruments, and they have also good tools based on those instruments that automate the process. And we don't have that yet for machine learning. And I think the future of aviation dependent on planes not crashing, and the future of internet on higher bandwidth and more stable browsers and a lot of other things, those all relate to each other in that way, that these industries are only the way they are because these measures were taken. And I think of course, there's other measures, but interpretability is one of the most important measures that can be taken to get machine learning where it needs to go. Lastly, this is a quick shameless plug about my book. It just came out. It's 14 chapters. There's Python code and a lot of visuals, but without excluding theory, which is very much needed to also be able to interpret the outputs. What makes it unique is that it covers both interpretation methods and solutions for interpretability issues, which is something not addressed in any book so far. Also, tax interpretation specific to deep learning and not tabular data. I also have avoided any hello world examples, and those use those toy data sets like Iris, and you know, that most data scientists have seen 100 times and lacking context. The reason for this is to use only plausible, fully developed example that have a backstory, which I call a mission. And in machine learning, you know, the how should never be disconnected from the why. Anyway, there's a exclusive discount for anybody that wants one. It will be active for only 1 month. You can print screen this if you're interested, or I can can paste it into the Q&A if anyone asks for it. Without further ado, now I'm ready for your questions, and I'll stop sharing right now. Thank you.
Thank you.